Hello, we are Group M7 of Quant Incorporated. Today we come to you from our R&D lab.
We've been tasked with defining new processing methods for the shackles of our high-performance padlocks.
So as most people know, the purpose of padlocks are to secure things. So for example, if there is a locker with contents within it that need to be secured, padlocks are often used for that application. So as you can see here, padlocks are made up of two main components, the shackle and the body. There exist two main types of padlocks, one which is the combination and the other which is activated by a key. So for the combination padlock, a specific combination is entered, and this will release the locking mechanism inside, which will release the shackle. For the key, it is pretty self-explanatory. If the key is twisted, it unlocks the locking mechanism inside, which also unlocks the shackle. Since the focus of this presentation is on the shackle, we will not be talking about the locking mechanism specifically. So other than locking things and keeping people from tampering from contents behind closed doors, essentially, the shackle must be able to withstand any sort of cutting or a high force on it, such as bolt cutters or saws. Also, the U-shaped geometry is what allows it to latch onto certain things such that they are secure. And the U-shaped geometry can be of different diameters. The height of it can be at different height, and these legs here can be spread to different widths.
For the geometric construction and design of the padlock, we chose a U-shape. The reasoning for this U-shape is to easily latch onto a plethora of objects, as it can be easily threaded through holes. This design is relatively compact as well, as there's no edges sticking out. This U-shape can be of different lengths and widths based on the purpose of the padlock. A larger diameter shackle is more secure, as there's more material to cut through. However, the smaller it is, the more versatile it is, as you can thread it through more objects. So in this case, we chose a 1 centimeter diameter. Also, if the lock is larger, it costs more to manufacture, so we took that into consideration as well. As a length, we chose 15 centimeters, as we don't want to make it too long, as more length gives more room for the shackle to be tampered with. And the shackle is notched at the ends to lock in place with the body of the lock.
In selecting a material to be used for the padlock shackle, the design specifications need to be considered. The shackle must be able to withstand large forces from prying, impact, and shear caused by bolt cutters. Because of this, most shackles are typically made of hardened carbon steel alloys. These materials are generally fairly cheap, allowing for shackles to be made at a fairly low price. If we allow the cost to be less of an inhibiting factor, we get a more diverse selection of materials to be considered. When selecting material, it must have a high tensile strength to resist deformation caused by prying and leverage. It must also have a high shear modulus. This is a material property that is a ratio of the stress to strain. A high shear modulus means that the material resists deformation when a shear force is applied. This is a critical attribute of shackles because they are typically under shear stress when people try to cut them open. Along with these attributes, the shackle must also have a high toughness. High toughness means that a material can absorb a large amount of energy from an impact without fracturing. This is important to consider since some materials can have a high tensile strength and shear modulus, however they can be easily shattered with a sudden force from a hammer. A low toughness would not make an ideal shackle, and thus a high toughness value is required. Even though this process was made possible by the reduction in the minimization of the cost, the selection must still be limited by an upper cost limit. In this case, it was determined that the shackle must cost less than $25, allowing for a premium shackle without too high of price.
So when it comes to manufacturing, there are several steps that take place within the manufacturing process of a shackle. So an oversized bar is initially received from the material supplier. So as you can see here, this shackle has a certain diameter, but the as received material is a much larger diameter than this shackle. The material is then either machined or cold worked down to this necessary diameter, and if it were to be cold worked, it was likely to be extruded into its round shape, or bar drawing is another common technique used to form specific diameter round stock bars. The length of the shackle while it is straight would then be cut, and then it would be bent into this U shape you see here. Following this, the notches that you see here on either side of the shackle are then cut. And throughout all of these processes, various heat treatments take place just to ensure that the shackle has the appropriate material and mechanical properties that are desired when it comes off the production line.
For the functional requirements of our shackle, we determined that the lock must withstand the tensile strength of a human pulling or prying at it, meaning it must have a high tensile strength. We chose at least 800 newtons for our minimum, and this was chosen based on the average weight of a person and the force of gravity. It must also withstand shear force supplied by bolt cutters, which is approximately 20 kilonewtons when 250 newtons is exerted at the handles by a person. So a high shear strength and a high shear modulus are necessary. The shackle must also have a high toughness, so it cannot be shattered by a sudden impact, such as the impact from a fall. And the shackle must have good corrosion resistance, so it can withstand harsh outdoor environments where it'll be in use.
To begin, it was determined that the cost of the shackle should be less than $25 per shackle. In material selection, the cost is priced per meter cubed. If the shackle was 15 centimeters long and 1 centimeter in diameter, to stay within the specifications, the cost per meter cubed would need to be less than $2.1 million. The U-shape geometry is also selected because it's easy to form through the bending of a rod, and is also the ideal shape for locking because its shape allows it to be slid into latches and used in many different situations. The bar length of 15 centimeters was chosen such that the shackle was not too small, but also not so large as to be expensive. It was determined that the shear force applied by bolt cutters would be around 20,000 newtons. With a safety factor of 2, the lock would need to withstand a force of 40,000 newtons. Considering a shackle with a 1 centimeter diameter, this required a material that could withstand 509 million pascals of shear stress. If we consider that the material should only deform by 0.1 millimeters when this stress is applied, the material would need to have a shear modulus of 50.93 gigapascals. It was also important that the material could have a high tensile strength relative to its density, such that the lock is not too heavy and cumbersome, although this is not as important as the shear characteristics. Finally, as mentioned before, the toughness of the material, and thus, passing all other requirements, the toughness must be maximized so that it will not shatter if it is hammered or impacted by a sudden force. At the start of the material process, the selection was narrowed to materials that have good tensile strength in relation to density. This was achieved with a slope of 1 and passing through a density of 1,000 and a tensile strength of 2.64 megapascals. Most of the materials passed this selection process. The next constraint was the material's shear modulus. As stated before, this required a shear modulus that is greater than 50 gigapascals. Thus, the materials were constrained to those that have a shear modulus above 50 gigapascals. Next, the cost was considered. With a cost of less than $25 per shackle, the cost per meter cubed must be less than $2.1 million. Finally, the materials that passed the previous selections were chosen based on the highest toughness value. High toughness is preferred because it allows the shackle to be unaffected by impact forces it sustains when people try to break it.
Based on the requirements from the previously mentioned design specifications, it was determined that SAE 8630 steel alloy would be an appropriate material for this application. So an oversized SAE 8630 hot rolled stock bar would be received from the manufacturer. This steel was chosen because it has a relatively low carbon content, which leads to a high toughness, which is important for this specific application. As previously mentioned in the manufacturing portion of this presentation, the bar is then cold rolled or machined down to the necessary diameter. Either way, this leads to internal stresses within the material. After the bar is cut and bent into shape, more internal stresses are induced. To alleviate these stresses, we chose to stress relieve the shackle by heating it to approximately 650 degrees Celsius for 1 hour, which is just below the A1 eutectoid line for an iron-carbon phase diagram. This ensures that no phase transformation will occur, but that the stresses can be still relieved. The legs would then be bent to the desired width in preparation for the next heat treatment process we chose, which is case hardening. Case hardening is diffusing alloying elements into the surface of a material such that the surface is harder than the rest of the body, consequently forming a case. In order to case harden the shackle, it would be placed in a high carbon environment, either with liquid or gaseous carbon surrounding the shackle. The shackle would then be heated to 850 degrees Celsius for 1 hour to transform the shackle to full austenite. Austenite has a high solubility limit of carbon, so a high concentration of carbon will diffuse into the surface of the shackle, which would be up to 0.7 weight%. The shackle would then be quenched in water to form BCT martensite at the surface. However, the surface would also be very brittle due to the martensite, so tempering is then required. The shackle would then be tempered to 200 degrees Celsius between half an hour to an hour to reduce some of the brittleness of the surface while not sacrificing too much hardness. Throughout this process, the core remains relatively strong whilst maintaining a high toughness, as its carbon concentration would have been approximately the same, so lower than that of the surface casing. The treatment is designed such that the carburization does not go deeper than 0.508 millimeters, given the relatively small diameter of 10 millimeters. The heat-treated shackle would then be stamped with hardened to say that it has underwent this hardening process.
The final finishing process we chose was electroplating with nickel. To do this, we clean the surface of the shackle with a solvent such as an acid cleaner. This removes oil and dirt accumulated during the manufacturing process and allows for a smooth, uninterrupted finish on the shackle. To electroplate with nickel, we put the nickel metal in shackle into a solution with nickel ions as seen in this diagram, with electrical contact between the two, and we run current from the nickel metal to the shackle. You see the electrons moving along here. Nickel ions then deposit onto the shackle to create the finish. This acts as a barrier coating for corrosion resistance, not as a sacrificial anode like zinc does in galvanization. So this just blocks the elements basically. This coating is more scratch and chip resistant than other coatings, such as zinc in the case of hot dip galvanization, as it's harder, and it's more scratch and chip resistant than painting and powder coating as well.
So as previously mentioned, we are Group M7 from Quan Incorporated. We appreciate your time for listening to our presentation about our optimized processing of our shackles for our high performance padlocks.